with uploading the videos. I think she's going to upload the 2 videos today after class. Go ahead. I already see something that I like more. We had a chance.
So can you see that now?
Yeah.
Okay. Wait for me.
We won't go anywhere without you. Let me just tell you this, guys, before you start. I'm also organizing a Quantum Hackathon. So the Quantum Hackathon, the same conference, I'm organizing another event there. Quantum Hackathon is very exciting. Again, the event is online. I posted the link on Slack. If you're interested, just register. And the format is very nice. So we have 4 online tutorials, and then you'll have some breakout groups for coming up with an idea. The nice thing is that one of the speakers is Guha, right? So MIT quantum father of many algorithm. And then there is a person from MERL, right? The Mitsubishi Research Center, that they do a lot of good quantum. So it's people that are really involved in devices. So if you're interested in quantum computing, quantum algorithms, quantum computer science, consider attending because it's very interesting and it's free. So go ahead, group
Okay.
Group 1.
So hi, we are group 1. Today we are going to introduce the dissecting attention mechanism and training transformers. This is our outline. Today we are going to introduce the cell attention, which is we finished at challenge 4, so we want to review this first. Second part is to discuss about positional encoding, and the next is about multi-head attention layers and mass cross attention, and some model evaluation change result.
Okay.
So I'll introduce about previous challenge. We use the cell attention mechanism, which computes some weight input, but in this challenge we use multi-head, so it's kind of different. And however, we didn't use the positional information, so
you didn't. Okay.
Some position encoding. So in this challenge, we are going to show some different from challenge 4. We use sine and cosine function, so to finish the positional encoding, and which can help us to give some information to label some numbers to different positions. These numbers have some mathematical transformation, and which satisfy some properties. You can see in this page. This page is about the explanation of positional encoding. Because we want to satisfy by the Phi transformation. The Phi transformation is some linear transformation plus some displacement, which is also linear. This is in mathematical a very good property, and if we use sine and cosine function, we can satisfy this property. And this is because sine and cosine function has the formula. If you use sine x plus with y, and you can write it as sine x cosine y and cosine x sine y, use like this formula. So in practice, a Phi transformation.
Let me stop you.
Okay.
Just a second. Euler formula. Open this web page. Euler formula. Just a second. Okay. Just a second. It's something small. Okay. Because you are young, so you need to know this. Good. So as an engineer, open this link for me. Yeah? So as an engineer, right? You never remember that formula that you just wrote. You always remember a Euler formula, which is basically allows you to remember all these equations without using your memory. Have you done Euler formula before?
No.
Yeah, so I think you guys do it I don't know when you guys do it. But basically, all these formulas of cosine and sine are very confusing. So next time, remember this formula, okay? Engineers always use Euler formula, okay? We, as engineers, our world is composed of complex exponentials, okay?
Okay.
Go ahead.
Okay, so in practice, a Fourier transformation can allow us to allow the model to learn more easy because it is some linear property. So this is why we use sine and cosine function to finish the positional encoding. So this is what positional encoding looks like. I use some simple codings to finish this different positional encoding with different frequencies.
Yeah.
And next, we're going to talk about the multi-head self-attention. Why we use a multi-head instead of a single attention head? Because that a single score dot can capture one kind of relationship, but in probably like the natural language exhibits may have lots of patterns, and that multi-head self-attention can project our values into multiple subspace in parallel, and letting each head specialize. And now, if we can see how this yields richer representation without raising overall complexity. Next page. And let's recall about the core building block. We will take our input embedding and form Q, K, V matrix. We compute raw scores by dotting Q and K, scaling by dk to keep the gradient stable, and then apply softmax to get attention weights. And finally, we'll weight V by these scores. And this this version is elegant, but will be limited expressly. This is single head. And next page is multi-head attention. We'll create H separate projection of Q, K, V via learn matrix W. And each head run the same attention procedure on its projected subspace and outputs dimensional results. And we then concentrate all heads outputs and then apply final projection W, O to return to the dimension. And in practice, the common choice are probably 8 heads, and the dimension will be like the next page.
Yeah, because the model has a lot of parameters, right? You see the dimension. Can you go back one slide?
Okay.
You see the dimension of these matrices, right? So they're all big matrices, right? So the model is very heavy when you have this many attached. Go ahead.
And I probably forgot to put one thing off, is that this construction will preserve the model dimension while letting each heads focus on different slice of the representation space. Okay, and next page.
We're missing a student. Who's next, guys?
Or probably I'll just talk about this. Add a norm is like applying a residual connection across layer, then perform layer norm.
I think the student is back, yeah?
I'm back.
Okay, 那你来讲.
My microphone was down. Sorry.
No problem.
So add a norm means to apply a residual connection across layers and then perform layer normalization. So residual connection can help retaining input features and facilitate gradient propagation. This alleviates the vanishing gradient problem in deep networks like the transformer. And layer normalization refers to normalizing all elements within a single sample. In this case, the sample typically has the shape of embedding dimensions times number of tokens. The stabilizing values helps ensure the consistent activation because the value are not the value before activation function will not be too big or too small. So we can ensure if we are using a sigmoid function, then we can avoid the gradient to be 0. Yeah, so which in turn facilitates smoother gradient flow and accelerates convergence. Okay, next up.
And we'll talk about the position-wise feed-forward networks. For each attention residual and layer norm blocks, the transformer applies a small 2-layer forward network at every position. And we can call it position-wise because it treats each token representation independently, and it injects additional nonlinearity and expand the model capacity to transform representation. Next page. And here is the mathematical formulation. The FFN formula shows 2 linear transforms with a value between. First, the XW plus B1 projects from dimension to dimension FFN, and the max apply value. And finally, we project back the dimension fields W2 plus B2, and all positions are share the same W1 B1 W2 B2 with a layer, but each layer has its own parameter. Next page. And then in contrast to attention, the complexity per layer feed forward runs in a big O of multiply D multiply dimension FFN and linear in a sequence length. Because it's operate independently across tokens, it's fully parallel across in N positions. And it's just 2 dense layer with non-linearity, so providing an expand and contract effects that enhance the model's representational power. Next page.
So I want to talk about why this network is position-wise. So because within the same layer, all positions share the same meaning across dimensions. So this feed-forward network is serve as a reorganization of the semantic meanings of the previous dimensions. Therefore, the transform doesn't need to be different across positions. Yeah. Next slide. So, masked multi-head self-attention is the core mechanism in the decoder. It incorporates a masking operation that prevents the model from attending to future position when predicting a given token. So this enforces the model to preserve the autoregressive property required for sequence generation tasks. Next slide. So as the figure suggests, a token at a given position can only attend to or access the keys of the position up to and including itself, but not any future positions. Next slide.
In this slide, I'll introduce what cross-attention is. So in the transformer architecture, cross-attention is also a key mechanism in the decoder. And its main idea is to let the decoder look at the encoder output while generating each output token. And this ensures that each output token is not only based on previously generated tokens, but also dynamically aligned with the entire input sentence, leading to more accurate and contextually appropriate outputs. Next slide. So here is this diagram shows how cross-attention works in practice. On the left side, we have the encoder block. It processes the input tokens and produces a key and a value for each token. And on the right side is the decoder. It first uses masked self-attention to manage previously generated tokens. Then at the T1 here, it produces a query from its own output, and this query will be used in the cross-attention step to interact with the encoder's outputs. Next slide.
Just a second. So you said the T1.
Yeah,
Repeat what you said about T1. I was looking for T1. Can you repeat?
So in this picture, we have T0 and T1. So at the T1 moment, the token 1 goes in and it generates the query in the decoder part. And so the query will match each key and value with the encoder parts. To
Let me just have so right. So because they are T0 prime and T1 prime, right? The decoder
Next
is
slide.
yeah. Go ahead.
Yeah.
Okay, go ahead. Yeah. So the decoder, that one there, T0 prime, the mask self-attention encoder, blah blah blah. Okay, good. Go ahead.
Okay, next slide.
Query Q1 is there. Yes. Okay. And
so here we can see how the query Q1 interacts with all the encoder keys, K1 through K4, and using dot product attention. And this produces attention weights, which are then used to compute a weighted sum of the value V1 through V4. And the result is a context vector summarizing the input information most relevant to Q1. And this context vector is passed through a feed-forward layer, which helps the model generate the correct next word. Next page. And here is the comparison between self-attention and cross-attention. And we can see self-attention is with the send sequence, and cross-attention, we cross between the input and output sequence. And the QK in the cross-attention part, we take from the encoder. The KV we take from the encoder, and the query part we take from the decoder. And in the self-attention, the sequence all take from the sequence itself.
Just a second. Let me parse. No. Let me parse a second. I'll go to self. Self cross within a cross. Query is the sequence. The correct output. KV sequence itself. Encoder's output. Applied in. Okay. So can you go? Yeah. So the encoder, the construction, you have the same. Okay. Good. Go ahead.
Okay. Next page. So why is cross-attention important? So it aligns output tokens with relevant input content, and it also enables accurate machine translation by focusing on the right parts of the source sentence. And it also supports summarization by identifying key information in the input. It also improves context understanding in tasks like question answering and dialogue systems. So to summarize this, cross-attention is the bridge that connects the encoded input with each output token. Next page. And on this slide, we'll look at how encoder and decoder cross-attention is implemented in our code. So here we have attention 1 and attention 2. And attention 1 is basically just a normal mask attention in the previous layer in the decoder part. So we take all the input K and Q and V as X and use mask. And in attention 2 is the cross part. So we take the K and V from the encoder output and X from the previous token, so which is the Q in the decoder part. So this is the difference between cross attention and mask attention here. Okay, next
Give me a
page.
second. Give me a second. Give me a second. Give me a second.
Okay.
Attention 1 takes the X. Attention 1 comes in. Attention 2 takes the X plus the encoder output. Since it's a multi-head attention 1, multi-head attention 2, the model. Okay. So the 1 itself XX, the 2 is X encoder, and then you have the small network, and then you have the dropouts. Okay, good. Dropout 1, 2,
Okay,
and
next
3.
page.
Okay.
So the linear layer of output layer is the transpose of the encoder-decoder embedding matrix, because multiplying this transpose is equivalent to computing the similarity between the output embedding and the embedding of each token.
Yeah, it's like an inner product, right? Because it's row and row times columns becomes a set of inner products. Yeah.
Yeah, so the result of inner product can act as a probability of that token, and passing through softmax can obtain a normalized probability. And
Vector, yeah, probability vector, yeah.
Yeah. Okay, next slide.
Okay, so here, whose part is this?
Okay,
Me. Thanks. Next page. This is the N-gram model to evaluate the and this is some formula for the N-gram model, and we can see if the times candidate match reference divided by the number of vocabulary in candidates, and we can get the evaluation score. Okay, and the next page, and but N-gram model is too ideal, so we should sometimes use clip count, and this is the times reference match candidate divided by the number of vocabulary in candidates, and by this manner we can get a more conservative and some more accurate condition. Okay, this way is better than the previous model. Okay, next page. And in our challenge, we use the bilingual evaluation understudy. I will brief introduce about the brevity penalty factor. This is some formula. If the machine-generated translation is longer than the reference, and we should get no penalty. And another condition, we should get some penalty. And by this way, we can. But the bilingual evaluation understudy is used to. Is used in the whole sentence, and the N-gram model is used in the lifetime translation. So different model used in different condition. In our code this time we use this condition, and the bilingual evaluation understudy is better. This is some condition, and we can. Okay. Yes, this is better. Okay, next page.
And here is our challenge result. Next page. Here is the task 1 with different encoder layers and head. And we did all the different encoder layers and attention here to see the trend accuracy and validation accuracy. And here's the all data for all different kind of layers and head. And basically we can show the next page. We can see that with more encoder layers and attention heads, the model will have better performance here. And here is our accuracy with different epochs, and here shows different encoder layers matched to different attention heads. And we can see that with
just a second, on the right, just a second, let me parse. Okay. So the color indicates the encoder layer, and the style of the line indicates the number of attention heads, right? So of course, so on the left-hand side, you have, yeah. Okay, so the results are always expected, right? So the more attention heads, the better the model is, right?
Yeah, with
But
encoder layer 6 and attention heads 8, we have the best validation accuracy.
But you just have that when you have the 4 attention layers, then the train becomes unstable. Is this average, or is this just one execution? Is it average?
It's only one execution. It takes like 20 hours to, I don't know, with training.
Of course.
Okay, so next
And
page.
that's why you also have 3 epochs, right? I understand.
Next page. And here is task 2. We have different encoder. We have same encoder layer and attention heads, but with different decoder layers. And here we use mask strategy and also unmask strategy to see if we let the decoder see the future token and not let it to see the future tokens accuracy and trend accuracy difference. And here's here's all the results we have. And basically, without masking, the accuracy is pretty high because you can see the answer. And with mask, it's normal. It's 0.5. And yeah. And next page. And here is BLEU scores with different decoder layers with the strategy our teammate just said. Next page.
Right, just a second. But here, the idea of the masking.
Yeah, we use mask and we take out the mask too.
No, I understand, but the idea of the masking. So basically, the point that I want to make is this, right? So if you're doing language generation, for example, right, then you will need to go masked, correct? So if you want to use it as a generative model, then you have to go masked, right?
Yeah, here we just want to see if without mask.
The penalty, yeah. So I understand. It makes sense, right? So basically, yeah.
Okay, so next page. And here's the result we have. The very good pies without mask and the normal pies with mask. And it's because we only do 10 epochs. And if we do more, it will just slightly go up and go to like 0.8 accuracy with mask. But it takes too long, so we didn't do that much epoch. But we can still see the accuracy going up slightly. Okay, next page.
Yeah, the masking accuracy is still increasing, right? But the other one already converged. Very good.
Yeah.
But now, wait a second. Go back.
Okay.
Go back. So here, it turns out that having fewer. That's the decoding layer. It's not. You change the notation, right? So now having.
Yeah, we change decoder layers, but it slightly affects the model.
Right. So here, having fewer decoder layers does better, correct?
Mm-hmm. Yes. Next page. And here is our.
Go slow. Go back a second. Let's reason. So why do you think is this? Because the size of the training is too short, or because the size of the dataset is too small?
You mean why decoder layers with fewer decoder layer will have?
Yeah, because of course,
here?
when you add a layer, right, there are so many parameters that you add to the network. and having to learn this parameter is very heavy, right? So you need a lot of data to train these sets. Go ahead. What do you think is happening?
We didn't. 林梦溪，你有想法？
因为有没有想法？
I think maybe because encoder layer is set to 4, so they have same amount of transformation. So the 6 will, if you do 6 in decoder, maybe it's likely to be less similar to the encode. Does that make sense to you?
No, I don't get what you're saying. So you say that the encoder has 4 layers. That's what you mean, right?
Yeah, he means we fix the encoder layer and head to 4 here. So if we have different decoder layers, we need to share the same encoder outputs, or we need to separate the encoder outputs to different decoder layers.
Understood.
And
Are you guys roommate?
yeah,
Always like this. Always people form groups, not based on merit, but just because they are roommates. You guys are so predictable to me, you know? I don't even need a... Yeah. You guys are so predictable. Go ahead.
Before doing this, I was supposing that 4 decoder layers will have the best result here because we fixed the encoder to 4, and I think the same layers throughout the whole model will have the best performance. But here it just doesn't see like that, and you figure it out why.
Yeah, I mean, it's interesting. Yeah. I mean, these models, they become so large that, you know, there are so many training dynamics that it's like you really have to have some experience to understand what is happening, right? Yeah. Go ahead.
Okay, I wanna ask, so with standard configuration, the encoder and decoder layers are the same. Is there a reason for that?
It's all black magic, right? This stuff is all magic, right? So when it comes to this type of hyperparameter choice, people have just a lot of experience, you know. It's that's what it boils down to.
So
Okay.
does my conjecture about the decoder layer mismatch, does that make sense?
Yeah, it makes sense. It makes sense.
Okay.
Now that your roommate explained it a little bit better, it makes sense.
Okay.
Oh, so we continue to the next page.
Go ahead, guys. Go ahead. Yeah.
Okay, so here is the task 3 with different scheduler. We have the original paper one with VAS1E scheduler, and also the constant scheduler and exponential decay scheduler. And here's the result of 3 different scheduler. We have the best one is the original VAS1E, and constant is almost done very good job here. But the exponential decay here is very bad. I think it's because we set the learning rate too small at the beginning, so it drops really fast, so it doesn't even learn here. And we fix the layers to 444 here. Next page. And here's the result plot.
So, it's a good question. What does this VAS1E scheduler, what does it do?
It's basically just using the add-in thing.
The beta parameter in Adam to decide, right? Something like that.
Yeah.
Got it.
Next page. Okay, so this is our perform. And thank you. And this is our challenge result. We done it. Thank you.
Any questions? Yeah, it's good. Good. Let me ask you guys. So for the final project, do you know what you're going to do for the final project, guys? Tell me a little bit. Guys?
we attend your challenge as
Okay.
Signal Ninjas.
So you're the Signal Ninjas.
Yeah.
Did you get? Did you like your name? I didn't want to. Yeah, I didn't
I didn't
realize.
even think that's racist or something. After you
I
say
understand
that,
that, like, if you.
I realized that.
It's very fun.
Oh,
Yeah.
it's very funny.
Very fun. Okay, very good. So for the Signal Ninjas, did you go through the challenge documents? I think we're trying to do our best there. Yep, very good. And you guys are still the same people, right? 5 people working together. I saw everybody. Do you guys want to run tomorrow or not? Do you want some extra points?
I saw you in gym this today at 7 o'clock.
Why didn't you say hi? Why didn't you say hi?
I
Why didn't you
I
say
don't know
hi?
how do I call you.
I mean, just call me whatever. It doesn't just whistle. It doesn't matter, right? I mean,
Okay, I'll say hi next time.
Yeah, I see. Don't be. I mean, I don't bite anybody's heads usually. So, but you didn't answer my question. Do you want to run tomorrow?
Sure.
Still 10 kilometers at that time.
I got class.
So you guys were also in my previous class. That's how you know that it's 10K, right? How do you know it's 10K, guys?
I've run it at your last class.
Exactly. So you did 10K?
Yeah.
Okay, very good.
I
So
think
you do
probably twice.
Very good. Come again? What did you say?
I do it twice, and I think it's very it's hard to run. It's hard to beat teacher.
Listen.
You run too fast.
Listen. I've had a baby and I was traveling for 1 year, right? So this is the right moment to shine. Okay, very good. So you guys are running 10K. All of you guys are going to run 10K, right? I'll give you a 0.1% increase of the final score. Is that okay?
When will be the?
I think tomorrow. I'm going to ask everybody, but I think tomorrow 6 p.m. What do you think?
You say how long you're going to run?
From 6 to 6 to 7. Yeah, 6 to 7.
Around how long distance?
10 kilo.
Roughly
Oh.
10K. Yeah, roughly 10K.
I think I can run.
Very good. So you guys just remember, take your phone, right? You can download some app. Either you use Strava or you use whatever app you like, and then you record how much you run, so that then you can post it on Slack, and we can give you extra points. Okay. So I signed you up, 5 people, 10K, 0.1 increase of the final grades. Okay. And if you see me, say hi. Okay. Don't just.
Okay. Okay. Okay.
Okay.
If I'm too tired, can I walk?
You can do whatever you want. Yeah. You just, I just fail you, you know.
Okay.
You take my class next semester. Yeah. Okay. Very good. Okay. Perfect. Okay. Let's go to the next group. Group 3, please. Is group 3 here? Hello, group 3.
Well, hi.
Hi.
So we are group 3, and because one of our member has got a flu, so he cannot speak for the presentation, and I will do this presentation for him.
Okay.
Okay, so hi everyone. this part of the project, I was responsible for building the full dataset preprocessing pipeline for German to English translation tags.
Can you speak
And-
German? Can you speak
No.
German?
No.
Can you speak English?
Yeah.
Very good. So you have to just learn German now so that you can evaluate the translation. Go ahead.
Okay, and we use a parallel corpus with each German sentence exactly aligned to its English counterpart. And the goal here was to take that raw text and turn it into something the transformer model could actually understand. That is, a clean and tokenized encode and structure input for training. And in short, the process looks like this. Raw sentence goes in, and clean data comes out, and finally into the model for training. For the text cleaning and label encoding parts, we have to do was clean the raw text, and that means removing weird symbols, emojis, and punctuation. Basically anything that will mess up the tokenization process. We also converted all text to lowercase to keep things consistent.
Do you know what the sentence means?
Sentence.
Yeah, this German sentence here. Do you know what it means?
No, I don't know.
Can you guess what it means?
Maybe it's delicious.
I love you.
Okay.
Then let me ask you, in the German language, you not only capitalize the first letter, you also capitalize what other grammatical element? So when you write in English, you capitalize the first letter of the sentence and
I.
and for I, yeah, and then proper names, right? The proper names.
Yeah.
But do you know what you capitalize in German?
Nouns.
All the nouns are capitalized. So you speak German?
A little.
Good. So you knew what the sentence means?
This means I. Ich means I. Lieber means love. Dich means you, but another form means object. You as object. So dich.
Dich. Yeah, it's a hard C. Ich liebe dich. Yeah, very good, very good. Where did you study German? Did you here?
Here, NYCU.
Did you go exchange in Germany?
Nine.
No. If you want to go, we have an exchange with Dresden. We have an exchange with TUM. Yeah, if you want to go, let me know. And because I did my postdoc in Germany, and you know what, I was visiting Germany last year. So if you took my previous course, I was teaching from Germany. So okay, very good. Go ahead, guys.
Okay, so then we added special tokens. For example, the start and EOS tokens.
End of sentence. Yeah.
End of sentence tokens, for every sentence. And we also measure each line in the German and English files matches perfectly so the model could learn correct translations. And this is the example, and the professor said, I love you, okay. So next, we needed to turn words into numbers. We create separate vocabularies and for German and English, and each token gets unique index, like padding, unknown, start and end of sentence. To keep the vocabulary from getting too huge, we dropped really rare tokens. This step was super important because once we had our token to index mapping, we could finally convert sentences into index sequence. also known as tensors, which is what the model needs. For the PyTorch dataset and data loader, once we had all the index sequences, I wrapped them into a custom PyTorch translation dataset class. For each sentence pair, it returned a triplet: the source tensor, the decoder input, and the decoder output. We then use data loader to batch the data efficiently. This also handled shuffling and padding automatically, so every batch was ready to go into the model without extra steps. This saved us a lot of time and reduced bugs during training. For the mask generation, transformers don't just need tensors, they also need masks. So I implemented two types: padding max and look-ahead max. The padding max stops the model from paying attention to pad.
Go ahead.
Uh,
You get lost.
the look-ahead max is used by the decoder to prevent it from cheating by looking at future work when predicting. These max were generated dynamically for every batch and passed into the model during training. Without this, the model just wouldn't learn properly. And a sample output batch. Here's what one sample batch looks like. You can see the source tensor, the decoder input, and the decoder output, all padded to a consistent length. And right next to that, we generate the corresponding max that makes sure attention happens in the right place. This entire packet is what gets passed to the encoder and decoder structure of our transformer. It's clean and ready to go. To summarize everything so far, we start from raw sentences, then we clean the text, tokenize it, and add special tokens like start and end of sentence tag. This prepares the sentence for indexing, batching, and attention downstream. It may look simple on the surface, but this stage is absolutely essential. Without it, the model just is garbage. For the process diagram part 2, next we will convert the tokens into index numbers using the vocabulary we built. We then pad or truncate sequences to ensure they are all the same length. And after that, we convert everything into proper tensors and generate the attention max. Once that's done, we are finally ready to feed the batch into the transformer model. And all of these steps together make up the complete pre-processing pipeline. And for the model structure, we will give it to the next person.
Okay, anyone see my screen? This one. Okay, I'm in charge of encoder, decoder design and the BLEU score estimation. So here, let's dive into our decoder design. Same as the encoder design, so we use one embedding to change word into some vectors. And the vector, how does it change, will be trained in each epoch. Then we use positional encoding to specify the position of words in the sentence. The difference is the encoder layer and decoder layer. Our design feature the built-in module of PyTorch. So this can reduce the complexity in coding. And for the output, the decoder features a linear layer and activation, just as the structure mentioned in Attention is All You Need paper.
Yep.
Then last, before we dive into these comparisons, let's discuss what does the BLEU score means. Let me change the window.
Mhm.
Okay, here is a brief example. So the input German sentence, das war ein Befehl. This means that is an order. But in many situations, the answer of the translation is not unique. So we can say that is an order. This is an order. It is an order. These are both correct. So we have one or more than one reference answers. And the model just output an order. So in the traditional n-gram score, we only found that if the words or phrases in the answer have appeared in the model output, but it will lead to another problem. We can find n and order both appears in the model output, but the sentence is too short and doesn't have the complete meaning. So we use the BLEU score to average the n-gram in different ends. We choose the n-gram from 1 to 3 to avoid too long phrases that is longer the sentence that causing error. So after choosing the BLEU score to analyze, we get this result. Let me change the window again. Sorry. Hence, we see the training loss.
What is happening here? Let me see. Let me see. Go.
The training loss, we can see that more complex.
Can you
What?
try to make the slide bigger? You're just sharing the.
Okay.
Yeah, try to click. Yeah, just try to figure out how to go in presentation mode. Maybe this one. Yeah, try. Okay. Good.
I'm not so familiar with Canva. Sorry. So we can see that it is beyond my expectation. Simpler model can have lower loss and more accuracy. And we can see that the BLEU score has strong correlation with training accuracy, just because we only have one set of the reference answer. So these two would be exactly not the same, but very close. And we can see the combination of 6 layers and and 2 or 4 or 8 heads. No matter the how much heads it have. Layers does more impact than heads. More layers, less accuracy and more loss. So I infer that the test doesn't require the much complexity to do.
How long was the training time for this? Because of course you guys just only did one epoch, right? What was the training time?
Training time for one epoch range from 10 to 15 minutes.
You could have done a few more epochs, right? Yeah.
We
Well,
have
you can see, yeah.
we have 2 epochs, two epochs here.
Yeah, I understand. Just it'd be nicer to see a little bit more training, you know?
And I have tried another thing with the same setting but 4 epochs.
Okay.
Under 4 epochs, we can either see the designs with 6 layers to converge. So more
Yeah.
complex.
So please put in the final report so we can see the full the longer training.
Thanks. So let's move on to the next part.
Hello.
Hello.
同样你分享吗？直接你进入 presentation mode 吗？这个
Yeah, you click on present. Yeah, go ahead. You click on present, and then you click present.
Hello. OK。诶 OK, next is 这个 attention heat. The attention heat map. The attention maxim allow the decoder to dynamically focus on the most relevant source position when generating each target word. It uses a learnable weights metric to create a soft analyzement, improve translation quality for long sentence. Multiple head attention capture diverse semantic
It's good.
pattern in parallel. Next we can see the heat map look like this.
Explain this one. Go ahead. Explain this one. Go ahead.
This quality post is the horizon. This is wait for a minute. For this, it is the refer to all position in source sentence. For this cross attention, it means it's also the same source corresponding to the same source sentence positions. But for this key post and post is represent all key position in first layer. For this diagram, we can see this is more light. Light. This is for more like it represent each query position in the encoder. It show the attention weights all over all the key.
You want to start over, or do you want to go ahead? Don't get what you're trying to say.
Okay. For this example, the light area, the bright area,
is the one with the highest weight, right?
This indicate that the model mainly aligns with the beginning of the source sentence for generate the initial target word.
But what is the length of the sentence, right? The sentences are pretty short, right? So how many sentences do you have that have more than 15 words? Not many, right?
For this diagram, this bright area is on the right side. It's indicate the model in it. This show the main concentration, the later half of the source sentence indicate that the model initial focus on the latest source word to translate the beginning for the target sentence. This is another different layer and different heat map. You can see that.
I think it would have been more useful. So this is average over the test set. How did you obtain this? Average over the test set?
What?
How did you obtain this heat map if you average over the test set? Anybody knows the answer in the group? Guys? Guys, how did you get these heat maps, right?
Get by we train the model and we get the attention.
So it's average over the test set, right? Correct? Is it correct or not?
I think so.
Because the issue is that like if you average over the data set, it's not very meaningful, right? What you can do is that you can take a couple of sentences, because the subject and the verb can be in different position, right? So usually when people do these heat maps, they take a single sentence to show the mapping between the input, the one input and the translation. So you can say, oh, this head pays attention to the verbs, this head pays attention to the nouns, right? If you just take the average over the data set, it's not very informative, right? Do you understand what I mean?
Yeah.
Try to redo it before the final submission. Go ahead.
static capture. This is another person's.
Yeah, go ahead and then go ahead, guys. Guys,
Okay, so I will cover the last part. I think, I think the person who are responsible for this does not show up. So
just show me what happens in. This is, go ahead, let's see.
well, and this graph is to plot the different architecture about the encoder layers with different encoder layers and different heads. We have 2, 4, 6 encoder layers and 2.
Yeah, but there is no learning here, right? So go to the next slide. Go ahead. This is go to the next slide. So let's see.
Next.
There was a slide that would look nice. Go forward the slides. Go to this 25. Go to condition 25. Slide 25. Let's remember. Slide 25.
25.
Yeah, show me 25. Okay, one back. Go back one. So then you
This is the text tree.
Okay.
About the comparison of constant learning rate schedule and the warm-up learning rate schedule.
Yep.
If the schedule type is warm-up, it uses a custom scheduler as following. At first, the learning rate increases linearly during the warm-up steps, and after that, it decreases proportionally to the inverse square root of the training step. And the purpose of this function is to control how the learning rate changes during training. So the training will be more stable. And here is the result. You can see the left graph is the constant learning rate, and it has a high volatility.
Yeah, there are some fishy numbers here, right? How can your accuracy be 99.9%? Right? Something fishy. Did you use a pre-trained model or?
I think yes. We have a high accuracy as well.
Go ahead.
And the right graph shows the warm-up learning rate, and although it is more stable, it does not reach the same accuracy as the constant learning rate. I think this is because it does not have enough effort for him to reach. Yes. We also compare the effect of padding masking on accuracy measurements. It computes the loss. The max loss function computes the loss while ignoring padding tokens in the target sequence. This makes the training more accurate by only focusing on real tokens and not the padding added for batch alignment. So we compare training runs with and without applying a padding max during the loss and accuracy computations. The results shows that when padding tokens are not maxed, we use padding max equals to false. The reported accuracies tend to be high. And this happens because the model is evaluated on padding tokens, which are not meaningful targets, but the model are easy to predict. So I think the model can learn to always output the padding tokens in those positions.
Okay, very good.
In contrast, when padding max is applied, a Rife graph, the accuracy reflects only the model's predictions on actual content tokens, which exclude the padding. While the numerical accuracy is lower in this case, it's more authentic and is more realistic and reliable indicator of the model's true performance in the left graph.
Mhm.
Okay, so that is all for the text 3.
Very good.
And that's all about our presentation. Thank you.
Very good, very good. Okay, so guys, yeah, so try to improve a little bit. Okay, this was not great, guys. It was not great. So tell me, how about the final project? Do you guys have any plan for the final project?
We haven't discussed it yet.
I think you should have discussed it last week. Yeah. Do you know do you have an idea what you want to? Okay, can you give me a plan by next time on what you want to do for the final project so I can give you feedback? Can you prepare a presentation on what you want to do?
Do we in the same group as this challenge?
Up to you guys. It's up to you guys. You guys decide. If you want to trade and change groups for the final project, that's fine.
Well, okay. And because we are struggling in finishing a lot of homework by every subject, so maybe we can discuss this week and with our group members.
Yeah, and yeah, I mean, I understand that you have, but the thing is that you're gonna put the final project deadline after the finals. So hopefully you guys will have some time to work on it. But that's why I wanted to mention it now, right? So that it should be now a month before the final exams.
Yeah.
Right. So you have enough time to think about it because you can. If you start doing the planning now, I mean, you should have already have a plan. But anyway, if you move with the planning now, you should be able to finish well. That's why I was suggesting everybody to join the competition because the competition started already last week. So you don't have to come up with a final project, right? You can just follow the competition that I was organizing. Anyway, so you guys are still the same, right? You guys are still 5 people, correct? Very good.
Yes.
Do you guys want to run tomorrow? Yes or no? You want to run for extra points or not?
I personally don't think I can run for like 10 kilometers.
No, of course. Just a best effort, right? Just best effort. You run for 1 hour between 6 and 7. You record the kilometers that you do, and then we give you we'll give you points. Go ahead. So one guy has the flu, doesn't matter. You try to come, and if you show up, then we'll let you run next week, okay? If you can run tomorrow, we can run next week. Sounds good? How about the others? These points are personal, right? So they're not connected to the group. One guy has the flu. Well, how about the others? But we will give him points if he show up and run next week. Okay, you guys decide. Okay. Anybody else interested? You let me know. I'll catch you a group deal if you tell me that you come all together as a group. I'll give you more points if you come as a group. Okay, very good. Let's do group 4. Actually, let's have a 10 minutes break. I'll see you back at 2:50, and we go with group 4. Okay. I'll see you back in 10 minutes. Okay, guys, 2 minutes and we start. Is group 4 here, guys?
Yes.
So if you cannot run at 6, you can run anytime this week. Just send the recording using Strava or similar. Okay, go ahead, group 4. You guys are still 3 people, right? Same 3 people? Group 4?
Yeah, we are still 3 people. And unfortunately, we haven't done this challenge in this time because we spend a lot of time for debugging the Python, and we spend all our GPU computing. So we can show our result. We still have some result, but we can
do it next week, right? You can show me next week, but I understand. Because the training is very long, so if you make some mistakes, then you throw away 2 days, right? So
yeah, we just debug for whole night and still cannot generate. So
no worries. Are you guys roommate as well?
No, we haven't met before. Yeah.
You have never met in person. Very good.
Yeah, never.
This is the youth of 2025. God damn it. Go ahead. Just show me something, and then you show me the final product on next week. There you go, no problem.
Okay, so， 对，你们不要那个，应该你们还在跑吧？
还在跑。问那个
那你们展示出来。
好像在彭医生那边，他的在。
哦，好。
Show me the other keys. Send your stuff.
So we actually do something, and we actually train the model. I think is correct, but we want to make it for a graph or show the more accurate data. So
of course.
Yeah.
I
we
understand.
may present it well next week.
Next week, no problem.
Yeah.
Okay, guys, then tell me about the final project. What do you want to do for the final project?
We haven't discussed it yet, so but I'm wonder, is there any instructions or requirement we should follow about final?
No. I mean, you guys are pretty much free to do what you want, right? You guys can try can decide what you want, right?
So we can do whatever that is related to this course, what we learned.
Yeah, I mean, like if you want me to give you some suggestion, if you want me to, I can try. So if you have done anything toward the final project, please by next week prepare a presentation of what you want to do,
Okay.
so that we can do it together, and then. Yeah, so if you, as I said, so I'm also running this competition. So if you want to join this competition, I can still let you inside the competition so that you don't have to think about it. Otherwise, yeah, so just give me a project and tell me how it's related to the class, and everything is fine. Just remember that, yeah, so it's the final project is a big part of the grade, right? So you really want to do a good job at it. Yeah, so you guys will have a month, and we will talk all together. We will have a presentation after the final week. But basically, yeah, so try to do well, guys. Try to do well.
Okay, I see.
Okay.
I understand. We will have it. We will discuss it later.
Okay, very good. Okay, so also, do you guys want to run tomorrow at 6 p.m.?
I personally, I'll try my best because
Okay, good.
I will have a meeting at 6:30, so I'm not sure whether it is
You can run 10 kilometers in 30 minutes and then go to your meeting. I think it's fine, right?
What distance should we run?
It's up to you. It's up to you.
Okay.
Of course, if you can keep, let's say, a Kipchoge marathon pace, that would be great, right? So if you can do like 3.5 kilometers per hour, 3.5 minutes per kilometer, I think it'd be great. Right? You can do everything in 1 hour. But basically, the idea is just to run together for 1 hour. Yeah. How about the others?
I'm free at that time.
Very good. Okay. And then there is another person. Is there another person that wants to come?
Still deciding.
What do you have to decide? You should be excited. You never met your other group mates, right? What do you have to decide? Are you busy?
Yeah.
Are you running a company? Are you raising a child? Just come run with us, right?
Okay.
So if you all come running, I'll give you a 0.1% increase of your final grade. Okay?
Okay. Okay.
Deal? Okay, good. Remember to record when you run. Okay.
Okay.
Okay. Last thing. Okay. Then we go. Stop your sharing, please. And then we discuss autoencoders. Okay. So just to recap. Okay. So next week, the group 1 is joining my competition, so they don't need to present. Group 3 and group 4, please give me some ideas about what you want to do for the final project, right? It could be 1 idea, 2 ideas, 10 ideas. We just discuss them quickly, and then we decide what to do in life. And if you change your mind, if you want to join the competition, I can still let you in the competition, even if the registration is ended. So if you cannot land on a proposal, you can go for that one. And then group 4 also will present. And group 3, if you want to improve your results and you want to present a little bit more and give us a better idea of what you guys did, I think it'll be better because the presentation today was kind of weak, honestly. And I think you guys can do better. Okay, very good. So now we're gonna do a little bit of transformers, lecture 25. And we're gonna do this. I'll try to teach for another 20 minutes and then to 30 minutes, and then we move on with our life. You know that I don't like frontal teaching too much at this stage of my life. Is there anything else that you guys want to discuss? You let me know. Huh? I'm trying to share. Do I have to go? Is there some sort of... Where is it? No. 25. Menu. View. It's full screen mode. Control, there is no full screen mode. Well, there's no full screen. Do we have challenge 6? Only 5. So I'm gonna give you a challenge 6, okay, for the next 2 weeks. But I will make it easy, okay? I will make it easy. I will try to make it as easy as possible, okay? I don't want you guys to hate me. Okay, good. Okay. Share, let's go transformers. Good. So remember the recap that we have done so far. No, not transformers, guys. I'm so dumb. Autoencoders, guys. Let me check. Did I get that right? Sorry, guys. My brain is a little bit lacking at the moment. Present. Window, Chrome tab, EAs. This one here, share. Okay, good. You guys can see, okay? Yeah. If I go into presentation mode, oof. That's not gonna be. Let me just figure out how do I go. How do I zoom in? It's not this. It's not this. I can also zoom in. Let me exit the presentation mode. 1 second, guys, right? Annotation 2, page view. Can I do the 1 page view? I do this. And then I do presentation. Does it look good? I'm trying to present from Chroma, but it's not working. So we just move to the downloads. It's gonna be easier, hopefully. So now we're here. Now we share VAs. Okay. Okay. Good. Now we're all set. We're recording. Let me double check that we are recording. Everything is fine. Okay. Good. Okay. So now we do a little bit of VAs. Okay. Good. So let's go to the motivation for variational autoencoders. Then inference in neural network. We're going to do some Bayesian linear regression, and then variational autoencoders and generative models. Okay, good. So what is the motivation for VAs? So you see that, I mean, now this is very much standard for us, right, to generate images. So for example, here there is a style transfer, right? So you're given an image of a statue, and you're doing style transfer from a pose of a person, right? So it's clear that there are many generative models that we are now exposed to. Okay, so this was, I think, this presentation was maybe 5 years ago, and you can already see all the generative models that were present there, right? So I'm sure you guys are familiar with this, right? So these are all the anime girls. This is for removing the background and doing tracking. Yeah? So again, style transfer from horses to zebras, classical example from maybe already 10 years ago. And then this is the Bach case, right? So there was this famous, again, beginning of the, say, 2010, there are all these transcription of Bach's sonatas, and you can have a generative model that produces Bach music, music in the style of Bach. And famously, there was an unfinished piece of Bach, and people trained the model to finish this piece in the style of Bach, and then a composer performed it, right? That was, again, 10 years ago. And now I think people are trying to escape AI artists and Suno and Spotify that uses AI-generated music. So these generative models really changed a lot. This is some AI for planning, right? So you want to generate house plans. Yeah, so this is also for generative, for generating signals, okay? So let's say that, for example, you have some experimental data which is too scarce. So what you want to do is that you want to generate a signal which looks as if it was generated by a certain source. And so you can train a model to generate signal that looks as if it's generated with a desired source. And then you can use this model for, let's say, testing systems or doing some diagnostics, so on and so forth. So VAEs, variational autoencoders, are a form of generative models. It's one of the first forms that people figured out how to use. Of course, this was all the rage back in 2020. So 5 years ago, you know, VAEs reached the peak of their, let's say, popularity and use in the ML. Now people moved on to transformer, to diffusion models, and to other AI models that are more state-of-the-art. But basically, this is a vanilla autoencoder. Okay, so the idea is that this is an autoencoder, right? So it encodes itself. So the idea is that you have X, and this X goes through a network, and you want to reconstruct the same X. You call it exact, and the loss that you have is between X and exact. So in a sense, the model only has one label. Sorry, as features, there are no labels. Because this is an autoencoder, right? So it encodes itself. Crucially, the shape of the network is this type of bottleneck network. So the idea is that you start from X, you produce an intermediate representation of X on a smaller space, which we will call Z. Then this Z is re-expanded out to the original size of X. So the idea is that what you can do is that you can use this intermediate representation of X, and you can impose some features, you can impose some constraint of this representation of Z, so that in fact you have a network that takes, let's say, a large input, produces an embedding of this large input, produces an encoding of these large inputs, and then this encoding is undone. So the idea is that in the representation Z, there is no loss of information, or there is a small loss of information because you train the network to reconstruct X itself. And by imposing different constraints of Z, you can have different encoding and decoding network that perform some desired task, right? So, for example, you can see how you could train this object to produce PCA, to produce NMF, to produce, let's say, some bit constraint representation of Z, and so on and so forth. Okay. In variation autoencoder, what do we do? Basically, we impose that this Z should look as if it's generated by a Gaussian distribution with a certain mu and a certain sigma. Okay, so the constraint that we impose, it's not on the single sample of Z, but it's, let's say, on a batch of Z, and the batch of Z should look like a Gaussian distribution. Okay, so why do we want to do this? So first of all, we want a continuous latent space representation. So you already saw with the NLP task, right, that you have a set of words that belong to a certain dictionary, to a certain bag of words. Actually, the computer is not particularly happy to work with discrete representation of variables. Computers much prefer continuous representation of spaces, so that there is let's say, the representation of the variable allows for differentiation. Okay, so if you want to differentiate something, if you want to be able to compute a gradient and train a model of a representation, then you will need to have a continuous representation. And then there is a very nice trick, which is called the reparameterization trick. We're going to see it later. And then we have a lower bound on the reconstruction term, which is called the estimated lower bound, or ELBO. Okay, ELBO loss. You're going to hear the ELBO loss a lot during this challenge. So why variation autoencoder is this way? So let's go through this. So let's say that somebody gives you a dataset X with n IID samples from some continuous or discrete random variable X, and we assume that there is a single random process that produces all this observation, and from observation to observation, there is the various observations are independent. Okay, so what we have is a dataset of random variables, and we would like to understand something about this random variable Z. Okay, so how we're going to deal with this, right? So the idea is that we could try to take a certain distribution theta, right, and try to obtain a representation of the latent variable X as the integral over the model of the conditional distribution, right? But this is clearly intractable because the number of data points is very, very large, and so you cannot imagine you can do a numerical integral over this many dimension and over this large data set. So what you do is that if you want to have this representation of the latent variable Z, what you could do would be to do some sampling, right? So you try to produce a sampler that produces the same distribution, or that the source Z is embedding, but of course this will be too slow, right? Because the dataset is so large that producing the correct sample will be too difficult. Okay, good. So what is the idea? The idea is that this Z random variable indeed represents some latent process that produces X, and we want to learn how to embed this distribution Z given the observed variable X. Okay, so it was invented. So yeah, so this is a funny slide, but basically it was invented by its own merit, and then people figured out that it could be there. So that's this slide is also very nice. So the idea is that there are some generative models. So these are models that are provided with random input, and they provide an output according to a desired to desired distribution. And then there are inference models. So there are models that can do that can perform inference, and the VAE are models that can do both. Good. So let's try to have a path that goes from a very classical topic, which is Bayesian linear regression, and it will take us around the map of ML, let's say, until we get to variation autoencoders. That's a plan for today. So let's go back and discuss Bayesian linear regression. So the idea is that, let me mute my phone. So the idea is, the people that didn't take my course previous semester, you can take it next semester, but the idea is as follows. If we use the bootstrap method, again, we saw it in the ML class, and we combine it with maximum likelihood, we can have a distribution of the coefficients of the latent variable. So this method is easy to understand. It is to understand, and it's provided as an analytical solution. Okay. So let's see what type of inference problem we have. Let's say that we have a linear regression problem in which we have an observed variable y, which is generated by x, and this model in particular is taken to be linear. So the f of x that we consider is a linear f of x, and you have this affine relationship, right? So you have b0 plus b1 x1, right? So there is an extra term that corrupts the observation. This is the epsilon, and again, since this is as a concept of noise which corrupts the observation, we can assume that the noise realization, they are all independent, and so there is nothing about x that we can learn from the noise. So we can always say that our true model is a linear relationship with the variable x plus some perturbation. And what we want to do is that we want to recover the coefficients, b's, that describe the relationship between the hidden variable x and the observed variable y. Very good. So, however large data set that we have, and however precise is our description of the real world, there are two sources of error that always arise in this inference process. So first of all, there is an error that corrupts the observation. This error is irreducible, right? And it's called aleatoric or irreducible error in the following sense. However precise your observation is, you cannot send the error to zero, right? The presence of error is a consequence of deep concepts in physics, right? No observation can be noiseless. This has to do, with you can describe this process in many ways, right? You can say that whatever measurement you take will be corrupted by some thermal error, and even if you try to remove the thermal error, then you will go down to the quantum limit, and even in the quantum limit, you will have the quantum undetermination principle, so you will never be able to observe a quantity with zero errors, right? So this is really a concept which is deeply embedded in the reality that we live in, okay? So there are no measurements that are not affected by error. And so this is called an irreducible error, okay? And this comes from many sources. And usually when the sources of error are many and varied, like in usually all measurement campaigns, then we can have some assumption such as the error is Gaussian because the law of large number kicks in, so on and so forth. The other thing is that what is called the epistemic error. And the epistemic error comes from the fact that when we choose a model, this model describes only some relevant aspects of the relationship between y and x. And of course, there are many other relationships that are not specified by the model. So, however, we believe that our model is correct, then we know that the true relationship between y and x are affected by other forms of relationships that we don't try to capture. Okay. An example for this will be, for example, the relationship between the acceleration and speed of the car, right? You can say that, well, if you apply this much acceleration of the car, then you're going to have this speed. But of course, what you're doing is that you are eliminating all the friction terms, so the different dynamic frictions, so the air density, the air temperature, the influence of many other variables on the friction of the asphalt and so on and so forth. And so, of course, specifying this this aspect of the model will not bring us knowledge or understanding of how the nature of the relationship is, but of course it's such that our assumption of a linear relationship between the acceleration and the speed is correct up to an epistemic level. Very good. Okay, so let's go back. So we're doing this. We're trying to catch this. Sorry guys, very confusing. Very good. So what we do is this. So we plot our variable x and our variable y. And what we do is that we try to perform linear regression. And over linear regression, we can obtain an estimation of the parameter B0 and B1 according to the dataset that we have. This is given to us in a closed form solution. And so we can say that this is the best estimate of our random variables. Okay, good. So now we have that we have a linear estimation of the of B0 and B1. The next question that we have is how confident are we of this estimation? Because of course our data is finite, and so the fact that the data is finite means that we only have a finite capabilities of estimating this variable. So what we can do is that we can apply some magic, right? We can imagine that we have 3 different universes. Over these 3 different universes, we have collected 3 different data sets. And we can see in the different universes what will be the exact value of B0 and B1. And if we have created enough universes, then what we can do is that we can obtain a distribution for the parameters. And from the distribution of the parameters, we can obtain, for example, an estimation of the variance, so that we can see what is the reliability that we can associate to a certain estimate of the random variable. Very good. Of course, we don't have multiple universes, so what we do is that we do bootstrapping. We take a data set, we randomly sample from the data set, we build the first estimation, we repeat, until we obtain a distribution of the parameters. In this case, we have B1, and we can see what is the distribution of B1 through this bootstrapping process. Okay, so bootstrapping is a fundamental concept, let's say statistical and machine learning, and it's what provides to you are the confidence, right? The distribution of the parameter that you're trying to estimate. Okay, so Bootstrap is computationally expensive. So conceptually, it's easy because what you do is that you just subsample from your data set, but it's computationally expensive because, of course, for each process, what you're doing is that you are rerunning the model on a portion of the data set. And so the complexity of bootstrapping is the number of samples of the model parameters that you have multiplied by the complexity of the algorithm to obtain them. Right? So if the algorithm is very complex, let's say as a training of a neural network with a few million of parameters, then you have to multiply this complexity by the number of samples that you want. Okay, good. So so we would so let's see if we can have some other approach. Let's see if there is some other idea that we can come up with. So the idea here is that we would like to have the distribution of the parameters B0 and B1 by looking at the data. So in a sense, what we are trying to capture is this posterior distribution expressed as follows. So we have the distribution of the data given the parameters. So in the world in which we live, there is a certain relationship between acceleration and speed, and this is the distribution of the data given the parameters. Notice that this is a distribution because there is the presence of error. So we're going to have maybe a deterministic relationship plus some random noise, and this will give rise to the distribution of the data. Good. Then we have the distribution of the data itself. Let's say if we went on multiple roads at different altitudes, there will be different distributions of the distribution of the different parameters of the models that links the acceleration and the velocity. And then you have the probability of the data. Okay, so if you have access to all the data, regardless of the parameters across multiple parameters, what will the data look like? Okay. So these terms we will call them like this. This is the likelihood. This is the prior distribution of beta, and this is the evidence. And what we would like to have will be the posterior distribution over beta. Okay, we would like what is the distribution of the beta given the data that we have. And the evidence, okay, is obtained from the likelihood by this integral, right? So this is just a Bayesian inference, Bayesian rule. So what you do is that you integrate over all possible model parameters, and you multiply the probability of the data given the parameters by the probability of a certain parameter occur. So what is the problem here? So unless you have some very simple distribution of the data, then the probability of the data is very hard to compute, because it is difficult to express the posterior as in closed form, for which you will need to perform inference. Okay, so of all these data, right? We might assume that the P of data given beta, we have some model, maybe some neural network does that, but this will be very hard to obtain this integration, right? Because the integral will require you to, let's say, take the different data, obtain the distribution, and then having a distribution of the parameters will be very tricky, because you will need a lot of data to do so. And so this mechanism is not particularly a problem, but there is a solution to everything. So what you can say is as follows, right? So if you drop this equality, right, you will realize that the denominator is just a scaling factor. Okay, so the denominator is a scaling factor. So meaning that as we change beta, right, this we will have a function. Okay, so the left-hand side is the function of beta, so beta is the variable. But in the denominator, right, we do not have betas, meaning that beta has been integrated out. So this is a constant which remains the same for all possible values of beta. So if you drop this constant, what you can say is that the probability of the data is always proportional, right? But is always proportional to the probability of the data multiplied by the probability of the parameters. Okay, so we can drop the computation of the difficulty integral by giving up the equality and just say that this is what you will call a generalized distribution, right? It's an object which does not, it's a distribution once you have dropped the condition that the integral over beta has to be equal to 1. And in practice, you end up with this model, right? And the probability of the beta given the data is proportional to the data given B multiplied by the probability of B. Then if you are given enough data, if you're given enough observation as a function of beta, what you can do is that you can compute the parameter C as the normalization constant that one has to learn. Okay. So let's go back to our linear regression example. What we can do is that we can assume that the B0 and B1 have some normally distributed priors, and we can assume that that they have a variance which is large enough for us to produce, let's say, a diverse enough observation. So this is what we have. So now we have described the probability of the betas. So this will emerge from the different universes in which we live, the different measurement campaigns, the different conditions in which you look at the relation between the car speed and the acceleration. And we want to get to this type of representation of the distribution of the parameters given the data as being proportional to the probability of the data given B times the probability of B. Okay. So when everything is Gaussian, what you can say is that the probability of an observation given B, right, will follow this distribution because the noise is Gaussian. So here you have the linear relationship between Y and X, and then you will say that the true observation Yn is the observation without the noise plus a Gaussian term. So this is the distribution of the observation given the parameters beta. Okay? So this is the input, and this is the label, and beta is a vector that contains the parameter B0 and B1. Then if you work out what is the distribution of the data, these are IID observations from this distribution. Since they're IID, the distribution of the vector is equal to the product of the distribution over each of the parameters in the dataset. So the dataset has an iterative, which is n goes from small n to big N. Small n goes from 1 to big N. And for each of them, you have an observation yn and an input variable xn. So this is a multivariate distribution of size n, where over each dimension small n, we have a ID distribution. Guys, going back and forth is very confusing. Apologies. And then what you do is that you also assume that the higher over the parameter beta is IID Gaussian. So you say that the distribution of the vector b0, b1 is obtained as a random draw from two IID Gaussian distribution. So this is the Gaussian distribution associated with b0, the variance sigma 0. This is the Gaussian distribution b1 with variance sigma 1, and they both have mean equal to 0. Okay? Of course, in this case, we have the assumption that the two parameters are independent, and this is just for simplicity. Otherwise, you will also have to consider the correlation between the two. So putting it all together, we have the distribution of the parameters given the data is proportional to the distribution of the data given the parameter and multiplied by the probability of the parameters. And since everything is Gaussian, this is just a nice little product. Everything simplifies. We can collect everything at the denominator, and when we collect everything at the denominator, we can simplify the expression. So this analytically could still be complex, but what we can do is that we compare how likely is a parameter across one realization and another realization using the equation. So this will be what you call the likelihood, right? So this is the probability of the observation B of I, B brackets I, and this will be the observation B bracket J. And as you notice, if I take this ratio, then the normalization constant C disappears. So I don't need to know the normalization constant C to obtain an equality here. So we are still dealing with Bayesian inference, but now we are not working with probability distribution. We are working with likelihoods. Okay. Now let's discuss sampling. Okay. So the sampling method used in Bayesian inference allows for the relative comparison between candidate points that are popular methods. And among the different sampling methods that people have invented, there are Monte Carlo sampling, and there is Markov chain Monte Carlo, okay, MCMC. And this is a very common sampling method. And among this sampling method, there is this very simple algorithm, which is the Metropolis algorithm, which is also called the random walk algorithm. And as you can see, this allows you to generate points according to a desired distribution. So let's discuss a little bit MCMC. So the Metropolis Hastings algorithm is very powerful, and the algorithm works as follows. Okay, so we are looking for the distribution of a parameter theta, and we want to reduce this problem to the sampling of the distributed distribution P of theta given theta to the following calculation. First, we make a proposal. Okay, so we have let's say a function with a mechanism that, given a past guess of the samples from the parameter, produces the next guess of the sample of the parameters. Then what do we do is that we evaluate the following ratio, right? We evaluate the ratio between the current proposal for the parameter theta and the past one according to this sample. So what you can do is that you can start with a trivial suggestion, with a trivial proposal. Let's say that you just take a normal distribution, and then you let this algorithm evolve. You let this iteration play out, and you will see that incredibly this results in a distribution theta, in a value theta that has the desired distribution Q of theta. Okay, so this is this is played out as follows. So we set an initial value, and then we do the following. We draw the next candidate from a certain, let's say, simple function that updates the value of the current candidate given the past one. We evaluate the ratio of sort of the fitness, right? We evaluate the likelihood of this current proposal versus the previous proposal. Then there is the following step. We look at this ratio, right? We look at this likelihood ratio, and if the likelihood is greater than 1, then it means that the estimation is improving, right? So then the current proposal it's more likely than the previous one, and so you update the proposal to the current one, and you already play out until your alpha is close to 0. And the last step is as follows, right? If your alpha is below 0 and 1, then you can accept the proposal or reject the proposal, and you do this according to a certain random probability nu, okay, which is another hyperparameter of the algorithm. So here we can specify things further. So for this proposal distribution, just take the new proposal to be Gaussianly distributed around the previous proposal according to a certain variance sigma, which is going to be your hyperparameter of the algorithm. And then for this accept and reject, what you do is that you just draw a random number between 0 and 1, and you see if this random number is above the threshold of 1 minus alpha. If that's the case, then you accept. So we simplify things. So then the key observation is that is the case in which Q is symmetric. So if this is a symmetric distribution, so that this distribution has the same function between the proposal and the previous and the proposal. So if this distribution is symmetric, and then if this happens, then what you can do is that you can simplify the numerator and denominator of the likelihood ratios. So you're just left with this likelihood, right? That the likelihood of the parameter given the data. Okay, so everything simplifies, and if you then this corresponds to just base here. Good. So the idea is as follows, right? So we have a certain data set, we have a current estimate, and we have a candidate generator. So we put them in together, and we see the likelihood of this given the past, and then we draw a random number with a certain random probability. Either we reject the new candidate or we accept it. Sorry, guys. And the rejection factor, as we said, is the factor that produces candidates is very easy. It's just a Gaussian distribution. And sorry, because the slides are driving me crazy. And then, yeah, if you keep operating like this, then what you obtain is that in the long run, the proposal is going to converge to the true proposal. Okay, so what you can do is that you can do an exercise that shows that if you want to generate theta according to one distribution, and you run the Metropolis statistic algorithm, and you achieve the correct distribution that you would have obtained with bootstrapping, but with much lower simplicity, lower complexity. Good. Now we want to scale this up, right? So it's clear that in this process everything was linear, the dimension was small, so it's generally uninteresting. But we want to retain this idea, right, of these Gaussian kernels. So what we do now is that we just replace the relationship from a linear relation to a neural network. So you will just say that there is some learnable network that maps y to from x, and this is just some network that you have trained, and as parameter w. Good. Then what you have to do, right, is that you have to show that the same mechanism works when you replace the relation between y and x with a neural network, and you will see that this is indeed the case. And we can also train this neural network because we can drop the dependency from basically the dependency from the parameter will now be the dependency. The previous dependency on the parameter b0 and b1 is now the dependency on omega. And so you have the previous proposal of the network parameters and the current proposal of the network parameters. So the idea is that this is only the forward pass. So here we're just evaluating, we're just generating a proposal from the network, but it's clear that we can also run this in backpropagation and also train the parameter omega. So now let's see the simplest Bayesian neural network, which we call the BNN. We have X, we have the two weights, we have one hidden layer, and then we have one output layers, and we have the observation. We say that the relationship between X and Y is going to be obtained through this very simple architecture, right? So hidden layer, output layer. Then this will be the forward pass. We set an initial value of omega 0. This is the initial weights of the network. Then you generate a set of candidates omega star according to this Gaussian kernel. You evaluate the likelihood. If the likelihood is greater than 0, then you accept omega star, and you update your proposal to the new proposal. If alpha is below 1, then you accept with a probability alpha, and you reject with a probability 1 minus alpha. So now we are given this data set for regression, let's say. And what we do is that we do this this MCMC training, and you will see that indeed what you can do is that you can show that you can train the network to learn the data distribution in this way. I'll let you go through this. This is just the exercise. Now we are heading toward the part with autoencoder. So let's go to part 2 very quickly. We do a little bit more, guys. We do the next slide on VAs, and then I'll let you go. VA part 2 of 2. VA part 2 of 2. And we download, and we load it up on Adobe, and then we share the network. Okay, we're good here. So remember what we were doing. We were here. We were showing the Bayesian neural networks. So remember that we went from Bayesian linear regression, then we substituted the linear kernel with a deep neural network, and now we are heading to variational autoencoders. So now we want to have an alternative method of estimating the posterior. I want to discuss variational autoencoder, variational inference, sorry. So let's say that there is a space of distribution, and there is a true E of W given D, a distribution of the weights given the data. And then the distribution could be very difficult, but what we want to do is that we want to find an easier distribution, which is easier to deal with, which is this Q of omega. And this is sufficiently similar to this P of omega given D. So what we want to do is that we want to be in a friendly space, right? So we want to have in a space in which we have some nice properties of this distribution. We have an idea of closeness of the distribution. We have an idea of smoothness of this distribution. And how can we define this, right? So for friendliness of the space, we can always take Gaussian kernels. So Gaussian kernels are really friendly to us. They decay very quickly. They are very smooth. So they have very nice analytical properties. We can take transform. We can take integrations. We know all the moments. So we like them as engineers. Remember that D represents the data. And we want to define an idea of similarity between these two distributions. And the idea of similarity comes from the KL divergence, the Kullback-Leibler divergence. Okay, and the Kullback-Leibler divergence is defined as D subscript KL, and this takes two distributions in input, Q and P, and they do not need to be they don't need to be. They can be they don't need to be univariate distribution. They can be multivariate distribution, and the idea is that the evaluation of the KL divergence will be this integral here. So this integral is not immediate to understand. It takes a while to convince oneself that this is really the correct way to measure similarity between these three distributions. And it takes the ratio of Q of omega. So Q of omega is the first distribution. On the denominator, we take the P. P is the second argument. And then we log this. So we log this likelihood. And then we weight it by the first distribution, Q of omega. and then of course we integrate over omega, which is the independent variable here. So this is not a distance, okay, because you can see right away that it's not symmetric. So the order of the arguments changing the value of the KL. So if I switch Q and P, I get a different value. And yeah, don't take it to be a distance. It's just a similarity measure. Some people sometimes they say they define it as a distance, but it's not a distance. It is always positive. It has the triangular inequality, but it's not symmetric, so it cannot be a distance. And so now we have this nice piece of distribution where we have an idea of closeness as measured by the KL divergence. And what we can do is that we can choose a family of distribution, for example, some normal kernel, and we can ask ourselves what is the closest, nicest distribution, so the closest, let's say, Gaussian kernel distribution that we have to our distribution of the parameters given the data. Okay, so basically we want to know what are the parameters of the Gaussian kernel such that the KL divergence between our closest kernel, right, our desired simple distribution, is small from the true distribution. And the idea is that in order to set up this problem, we will set up this as a minimization, right? So we will say that we want to minimize the loss, and this can be rewritten as the KL minus an expectation term. And the point is that in order to obtain this closest distribution, we don't have to do sampling as in the Metropolis-Hastings algorithm, but we can minimize the loss function. And this loss function is what we call the ELBO, okay? So now everything is in place, right? So we have a Bayesian neural network, and the Bayesian neural network produces the candidate, and we accept or reject. And what we can do now is to describe the backward pass. In the backward pass, what we do is that we update the weights of the network in such a way that we increase the fitness of the neural network that does the mapping from the X to the Y, from the input to the label. And basically here we will do it with multiple mini batches. In the backward pass, what we're doing is we're minimizing this loss function, which is the ELBO loss function. And yeah, and then we are able to run backpropagation normally. So the idea is that at the beginning, we will fix some true weights, but after this, right, we will have a distribution of the weights over the Gaussian kernel. So it means that we don't have single weights, but we have we don't have deterministic weights, but we have probabilistic weights. So we have a distribution Q of Y, Q of omega Y, that describes the distribution of the weights over the different bootstrappings. Very good. This is what we call a variational neural network. So the idea is that in a variational network, we assume the weight distribution Q of phi of omega that has parameter omega. Most often we assume this to be Gaussian, to be some sort of Gaussian kernel. In the forward pass, we do the computation of the activation, and we need to fix the values of the weight. Since in order to obtain the forward pass, we need this deterministic weight. What we can do is that we can just take a sample from the distribution Q phi of omega, and then this will give us some activation. And if we repeat this enough time, then the fact that we are doing this sampling operation does not harm the generalization of the network. So now we understand better this pass. Sorry guys, the mouse really is very sensitive. So the idea is that we have a distribution, we fix the distribution, we obtain a realization of the network. For this realization, then we can run the backward propagation, and backward propagation is gonna give us the mu and the sigma of the weights according to the loss that we've chosen, the ELBO loss. So now you have a little bit of a picture of the landscape. So you have Bayesian neural networks. They bring together MCMC. MCMC, they have the most famous is the Metropolis-Hastings. Other methods that are also sort of stochastic method to train neural network are dropouts and bootstrap. You have seen dropouts already in the course. Bootstrap. You should have seen it in the previous course if you take it. Otherwise, we just described it there. And then we have variational activation. So we can have stochastic in the union, and we can have variational weights, which is what we just discussed, which is sort of Gaussian can represent the weights. Good. So what is the end of this all? The end of this all is that we have deterministic input, we have deterministic weights, or we have a stochastic output of sigma. So the way in which we learn the latent representation of the variable y in variational autoencoder is in terms of the distribution of the y. So we will get the mean and the variance of the different entries of the y. Okay. Yeah, I think this is it. So the workflow is that you build the model, you define a loss function, you minimize the loss function. This is the variational method. So in the variational method, things will remain the same, but now when we build the model, we have probabilistic layers. So the layers are no longer deterministic, but they are sampled. The loss function is the negative log likelihood, and then we are still fitting the model in order to learn the parameters of the distribution of the kernel weight. And yeah, everything works through as you expected, and the result are variational autoencoders. Okay, very good, guys. Let's stop for now here, and then we update next week. And yeah, I'll see you guys soon. I'm going to be online if you have any questions. Otherwise, we stop the recording. Hi to the people of the future. And yeah, if you